All right, good morning, dear students. I'm sick, so I'll be recording this from home and giving you this video instead of a normal class. So I think we finished basically chapter 2.1, so let's start with chapter 2.2, which is actually about not an organic molecule, but nevertheless very important, the water molecules. So we tend to say that water is very important for living organisms and that we consist of about 60-70% of water, but it's not part of the biomolecules. So let's look at why it is so special and why it's important for living organisms. So water has the chemical formula of H2O. That means that there's two hydrogen atoms for every oxygen atom in the water molecule, and water has these amazing features associated with it. As you see here by the striders, that's what they're called, water strider maybe even. These insects are able to walk on top of water, but that's because water has this very high surface tension. So they're able to walk on top of it. And similarly, water is also able to adhere to certain surfaces like this one. So we would expect water to just fall down this blade of grass, but instead it actually is attached to it. So that's part of water's adhesive properties. Water is also cohesive. It means that it holds together to itself, kind of. So the water molecules seem to hold on to each other. Or the parts of the water, if you look at more at a macro scale, like this water bead. So the water seems to be holding on to itself instead of forming this long, maybe stretch that we would expect to see. Instead, it seems to form these beads. So that's this cohesive property that it has. So why does water have these amazing features? Now, one of the main theories behind why water has this property is explained partly by this property of certain elements, the electronegativity of certain elements. So this is the periodic table, as you might know, and the values here beneath each element, it's the electronegativity of the element. And we can quickly see that the electronegativity is very much lower here on the left side than it is on the right side. The noble gases, they don't have any electronegativity because they're happy. So basically, but these ones on the right, they have much higher electronegativity than the ones on the left. And if you go from the bottom to the top, you have also higher electronegativity in general. And the reason this value is related to it's a measure of how strongly an atom of this element attracts electrons. So electrons are, of course, the small negatively charged particles that are on the outermost part of atoms, and they're important for when atoms form molecules. So if you combine, for example, fluoride here, or fluor, it has the highest attraction of electrons of any given substance, and that's because this fluoride has 7 electrons in its valence shell, and you want to have 8 to be the most electrically kind of or energy-wise most beneficial state. So the lowest energy configuration would be if you have a full outer shell. So this one is very close to reaching that. On top of that, it only has 2 shells. So it has the first shell, the K shell, and it has almost full L shell, which means that the distance from the electrons to the positively charged core is very low. So the core is pretty good at then attracting new electrons. So in this case, there's a short distance between the core and the electron shell where a new electron would fall into, and it's also close to reaching this noble gas state where the outer shell is full. Okay, So you know also that sometimes if you mix, for example, a metal like lithium with fluoride, lithium then, which has very low attractance for electrons, will lose one electron and also become similar like helium in its noble gas state. And this electron will instead fall to the fluoride atom that will also reach this the same state as neon. So it's basically acting like a noble gas as well. And now they can form the ionic compound lithium fluoride, a salt basically. However, this is not the case. For example, if you mix carbon and hydrogen, the difference between these values is very low, which means that electrons are shared more equally. So these compounds don't, the electrons are basically sharing their time between carbon and hydrogen quite equally. However, if you take hydrogen and oxygen has 3.5, this one has 2.1. So the difference is quite high actually, which means that when the molecule water forms, the oxygen kind of attracts the electrons very strongly, and it means that the electrons for hydrogen seems to spend more time on the oxygen side, so the oxygen side becomes weakly negative. So this is what this one shows. So this is the structural formula or planetary formula of water. So this is the K shell, this is the L shell then of water. So one of these electrons here in this bond is from the hydrogen and one is from the oxygen. So the one that hydrogen gives up here, these two will spend more time on the oxygen side. So it means that the oxygen side becomes weakly negative, whereas the hydrogen side becomes weakly positive. And this means that this molecule is polar. It means that it has two poles, a positive and a negatively charged pole. Since it has one positive and one negative, we tend to call it a dipole. I assume you can also get molecules that are more complex with more element or more atoms that are then maybe tripoles and so on, but I don't know. It's not important for us. But water is a dipole. So each water molecule is negatively charged on the oxygen side and positively charged on the hydrogen side. Not as much as an ionic compound, but more than, for example, methane, CH4. And the idea is that water gets its cool properties because if you imagine that if we put several water molecules together, you'll have some of them, you'll be able to get attraction between the positively charged side of one and a negatively charged side of another one, meaning that they will attract to each other, whereas maybe the two negative sides will kind of repel each other. And that means that there are forces basically holding the molecules together. We call these dipole-dipole bonds. They're not real bonds, they're electrostatic interactions between them. But the idea is that this intermolecular bond forms between the molecules, and that kind of gives the cohesive properties of water. And we can see, so we don't know for certain that these kind of things happen, but this hypothesis kind of bears out in all kinds of experiments that we have. We can't observe this directly, so we have to infer it from experiments and hypotheses. This is basically how we do most science, actually. But for example, this property means that water has the ability to move up through the stems of plants. So this is how water. So plants have these vessels inside of them, where water moves from the roots up to the leaves. So even a tree that is maybe 100 meters long, it doesn't actively pump the water from the roots to the leaves. It actually flows up there by passive forces. And that's because of this cohesive property of water. So there are two actually things happening here. Water molecules are able to adhere to the sides. This is the vessel shown here. So water molecules are able to adhere to the sides, meaning that they won't fall down. And on top of that, when water evaporates from the leaves, water from within this system will move into the leaf. And since there's attraction between this one and the next one, this one will move with it and so on. And then will transfer it down the whole line, meaning that the water will move as a cohesive unit through this whole system. So this adherence to the sides and this cohesive movement, cohesive property, means that water can move passively from the root up to the leaves of plants. So that's a very important aspect of water. Water also has some other interesting features because of these dipole-dipole interactions. It has high specific heat capacity. It means that you require a lot of energy actually to heat up water, but it also means that water loses energy very slowly. And that means that it kind of doesn't shift in its temperature very rapidly. And that means that it forms a quite stable environment for organisms to develop and exist. So if we imagine on land, the land heats up quickly and it cools down very quickly, the air on land. In addition, water has this very strange density curve with temperature. So the density of water is highest at temperatures about 4 degrees, which means that colder water, meaning ice, floats, and water that is liquid is actually less or more dense, that will be at the bottom. So this means that we also get a protected, so this ice actually protects the rest of the water. So it means that we have once again a very protected environment. So this is why liquid water may aid in the formation of life, because you have these protected environments. So that's one of the reasons why when we're looking for planets that life could exist, we're looking for planets with water. And this kind of dipole-dipole bond that exists between water is actually a form of a hydrogen bond. So hydrogen bonds are specifically, or are specific types of dipole-dipole bonds that exist between hydrogen as the positive side on one molecule, and oxygen, nitrogen, or fluoride as the negatively charged part of another molecule. So these are special because if we remember the electronegativity here, nitrogen, oxygen, and fluoride are the ones with the highest electronegativity, which means that they attract the hydrogen side most strongly, so to say. So it has the highest, weakest, or negative side. So it means that they are a bit stronger. So specifically, the dipole-dipole bond in water is a form of a hydrogen bond that is formed. Hydrogen bonds are very important. For example, we're going to look at DNA later, and between the two sides, the nitrogen bases in DNA, thymine, adenine, cytosine, and guanine, we have these two sides of the DNA molecule are held together by hydrogen bonds. And we'll see that thymine always, I think these are Swedish actually, so sorry about that, but thymine and adenine always go together because we can form 2 hydrogen bonds here, whereas between cytosine and guanine you can form 3 hydrogen bonds. So they are specific for each other because they form the right number of hydrogen bonds. Water also has the ability to dissolve polar compounds, such as here sodium chloride, which is an ionic compound of your regular table salt. If you put that in water, the crystals, over time, they will dissolve into the water. And that's because, once again, the polar properties of water in this crystal compound, or in this crystal of salt, there have positive and negative ions, and the negative sides of the water molecules will surround and dislodge basically so the negative sides of water will be attracted to positively charged ions and kind of rip them away from this salt, and it will become smaller and smaller, and the whole thing dissolves. Same thing happens with, for example, sugar. So sugar also forms kind of a crystal structure, but it's because sugars are also dipoles, and they can also be dissolved in water. So the solvent properties of water is because of the dipole nature. And interestingly, if you then instead put hydrophilic compounds, polar molecules, will dissolve, but hydrophobic compounds instead will attract, even though they don't have any specific force that brings them together, the water molecules won't like to be close to them, and they want to form hydrogen bonds with each other. And the maximum number of hydrogen bonds that can be formed is when these hydrophobic compounds are pushed together. So these compounds move around in the water all the time. All the molecules move around all the time. And when these come together, they will be pushed together by the hydrogen bonding of the water around them. We call this hydrophobic attraction. And in the book, they show you these ones. These are two non-polar kind of particles in water, and there are more hydrogen bonds formed in this situation than in this one. That means that these two will these two non-polar molecules, they will be pushed together by the water basically and attract to each other. So this is if I'm correct, this should be the reason why, for example, fats are pushed together in water. Water is in blood is for the most part consistent of water. So your blood is to 55% plasma, and 45% is of the water is cells. And of this plasma, about 90% is or more is water. So water is very important in blood, in that it's able, blood, for example, moves around heat in your body, and it dissolves lots of nutrients and gases. So, for example, carbohydrates are transported in blood because by being dissolved in the blood plasma, and that's because they are polar. Amino acids are also transported in blood to different cells, and many of those are dissolved because they're polar, but some others are transported in proteins. Fats like cholesterol and other lipids are transported also, but they're not dissolved in water. Oxygen is also transported by the plasma, but partly dissolved and partly bound to hemoglobin, etc. And carbon dioxide as well is bound to hemoglobin, and some of it as ions, and ions like sodium chloride also is transported in blood as they are soluble. So this kind of property, the polar property of water and its heat capacity, makes it good at performing the jobs it's supposed to do, transporting heat, for example. And the heat capacity of water also makes it good to be able to cool the body off. When your body becomes hotter, receptors in your brain kind of notices this and initiates expansion of the blood vessels close to the skin, which means we'll start sweating more. And as the hot water is on the surface of the skin, some of it will evaporate, and when it evaporates, it brings energy with it, and that leads to your skin cooling down by evaporative cooling. So water is super duper important as giving the kind of properties that it has to give the circumstances for life to form, and it's important as a transport medium, for example, both in cells and in your blood, and it's good for us to be able to cool down as well. And I think that's all we wanted to say about water. So I'm gonna finish this video and say goodbye.